Building a highly available cloud environment often requires weeks of planning. Today, we'll build a functional canonical microcloud cluster from scratch in just minutes. Welcome to the tutorial. Traditional data centers frequently struggle with cloud sprawl, underutilized hardware, and unpredictable licensing fees. We're going to bypass those hurdles by setting up a lightweight, repeatable architecture designed for edge computing and distributed workloads. Before we touch the command line, let's look at the hardware. For a test or development environment, MicroCloud is lightweight. You can start with a single member deployment and as little as 8 gigabytes of RAM. This diagram compares a test setup to a production environment. A highly available cluster requires 4 physical nodes with 32 gigabytes of RAM and 10 gigabit network cards. Within each node, allocate 3 NVMe disks for the OS, local storage, and distributed Ceph storage. Separating these disk types and maintaining a 4-node count provides critical redundancy. If one node goes offline, the extra member prevents a split brain scenario, where remaining nodes lose synchronization, ensuring applications stay reachable. Step 1 is the operating system. Every server you intend to use in the cluster must be provisioned with an Ubuntu long-term support release. Once your servers are ready, you'll need to install the core services. On every node, run the command sudo snap install microcloud lxd microceph MicroOVN. Installing these as containerized snaps keeps the host operating system clean. Because all dependencies are bundled within the snap, you avoid the traditional conflicts between different package versions. Now we establish the cluster. Choose one primary node to serve as your initiator. SSH into this machine and run sudo microcloud init. The wizard will ask if you want to set up more than one cluster member. Select yes. When the table of available network interfaces appears, choose the specific IP address you want to use for MicroCloud's internal cluster communication. The initiator terminal will generate a secure passphrase and enter a waiting state. Leave it running. Open new SSH sessions into your secondary nodes and run the command sudo microcloud join. On each secondary node, select the corresponding internal IP address. Enter the passphrase generated by the initiator and verify that the unique fingerprint matches what you see on the primary screen. This simultaneous handshake automates the distribution of trust between nodes. It removes the need for manual SSL certificate management and private key distribution across the cluster. Return to your initiator terminal. You will see a list of the secondary systems that reached out during the trust session. Select all of them and confirm to formally accept them into the cluster. Next, we move into the storage configuration phase. The wizard will prompt you to set up local storage pools. Select yes. You will see a list of available disks from across the cluster. Select exactly one designated disk from each machine to assign to the local storage pool. Pay close attention to this requirement. Any disk you select for these storage pools must be completely unpartitioned and free of existing file systems. If you attempt to use a pre-formatted disk, the initialization will fail. You would then have to manually wipe the drives and restart the entire setup from the beginning. After local storage, the wizard moves to distributed storage. Select yes, and then choose at least 3 unpartitioned disks across the cluster. MicroCeph requires at least 3 disks to properly replicate data for high availability. You can then choose several optional configurations. The wizard allows you to wipe existing data on the disks, set up a Ceph-SF distributed file system, or enable disk-level encryption. This storage strategy allows you to pair the high-speed performance of local hardware with the resilience of a distributed cluster. You can run intensive edge workloads on local caching, while your primary databases remain replicated and protected. With storage locked in, we move to the network configuration handled by MicroOVN. This provides a software-defined network that allows your virtual machines to communicate across the cluster. Select Yes to configure distributed networking. The menu will display your physical network interfaces. Select one interface per machine to act as the external uplink. Note that for distributed networking to function correctly, the selected uplink network must support both broadcast and multicast traffic. Next, provide the IPv4 gateway for the uplink network using CIDR notation. CIDR is a standard format that pairs an IP address with a suffix indicating how many bits represent the network prefix. Finally, the wizard will ask for a range of IPv4 addresses. Define a specific block on your network that will be reserved exclusively for your LXD instances to use. There is one common failure point to keep in mind. MicroCloud uses MDNS, or multicast DNS, to automatically find the initiator node on your network. However, some restrictive cloud environments block this traffic. If the secondary nodes cannot find the initiator automatically, you can manually input the initiator's static IP address. This bypasses the discovery phase and allows the handshake to proceed. Once you complete the remaining prompts, MicroCloud will begin the automated bootstrap. It will now configure and launch all the requested services across every member of the cluster. This automated bootstrap effectively handles the technical heavy lifting of networking and storage orchestration. It turns a complex infrastructure deployment into a repeatable, scripted process. Monitor the terminal output. When you see the final message stating MicroCloud is ready, your multi-node cluster is live and fully synchronized. While you can manage every aspect of the cluster via the command line, you can also enable the Canonical LXD graphical user interface for a more visual management experience. This LXD dashboard provides centralized control. The left menu manages instances, networks, and storage pools across all nodes. In the main console, a live Ubuntu desktop instance confirms our compute, network, and storage layers are actively working in unison. This architecture provides a scalable foundation for hybrid cloud management. It allows you to pair the visual agility and rapid deployment of a public cloud with the security and cost control of your own on-premise hardware.